Okay, let's begin with the topic of computation space topology. Okay, till now we have talked about in viewpoint of the number of degree of freedom of a robot's computation space. Okay, let's turn into the uh, viewpoint into the shape. Uh, okay, in the viewpoint of the shape, it is called as a topology in academic terminology. Okay, the two configuration spaces are topologically equivalent if one space can be continuously deformed into the other space without cutting and gluing. The key point is the concept of a topological equivalence does not use the cutting or gluing. Okay, let's consider the sphere and the football. Maybe you know the football is oval shape ball. Okay, the sphere has the same radius. Okay, the sphere can be deformed uh, into the football simply by stretching without cutting or gluing. Uh, okay, these two spaces are topologically equivalent. We can make it by just deforming or stretching or contracting, something like that. Then we can make the sphere into the football or football into the uh, sphere. On the other hand, let's consider sphere and the plane. In this case, we cannot turn the sphere into the plane without cutting. Is it right? We should cut the surface of the sphere, then we should stretch to make the plane and extend. So the cutting is required to the change from the sphere into the plane. So in this case, sphere and the plane are not topologically equivalent. In the mathematical way, sphere will be denoted by the S and the plane will be denoted by the R1 and R2 and R3. Okay, so those are the origin of those different to each other. Okay, topologically distinct one-dimensional space include circle. Circle can be extended to the surface of the sphere. The line can be extended to the plane, and the closed interval of the line. We have the three kinds of distinct one-dimensional space. Okay, circle is denoted by S or S1. As mentioned before, the the surface of the sphere will be denoted by the S2, two-dimensional sphere. Okay, the line will be denoted by the E or R because in order to denote the Euclidean number, we will use the real number. So E and R is interchangeably used. Okay, the Euclidean surface space. Okay, the line is the one-dimensional Euclidean or flat space, not circle, because the point in the Euclidean space is usually represented by the real number, so it will be denoted by R instead. On the other hand, as a third item, the closed interval of the line, it will contain each endpoint. It is different from the line. Line does not have any endpoint, but the closed interval of the line has the finite endpoint. So it can be written as bracket A to B bracket belong to R1. Okay. In higher dimension, Rn is the n-dimensional Euclidean space. Sn is the n-dimensional surface of the sphere in the n plus 1 dimensional space. Okay, let's take an example. S2 is the two-dimensional surface of the sphere in the three-dimensional space. Can you understand the surface of the sphere? It will be denoted by the S2. Okay, no, it is noted that the topology of the sphere is fundamental property of the space itself. So it is independent of how to choose coordinate to represent the point in the space. Okay, the topology does not take any real number actually. So the topology is the much bigger the concept without adopting the number system or coordinate system. Okay. Okay, the open interval of the line, it is not basic element of the basic element. It's not basic element. So the open interval of the line does not have any end point. So let's extend by attaching the end side. Let's just extend the line, open interval line. Then we can get the line because it does not have any end point. So line and the open interval line are topologically equivalent. Is it right? That's true. On the other hand, a closed interval of the line, it cannot it does have the end point, so it cannot make the it cannot be changed into the circle or line. So closed interval of the line is the basic element of a topological space. Okay. Some C space can be expressed as the Cartesian product of the two or more space of the low dimension. So it means the point in such space can be represented as a union of the representation of the point in the low dimensional space. Okay, let's take the example. C space of the rigid body in the plane. Maybe you know the rigid body in the plane will be expressed by the coordinate x and y. It will be denoted by the R2 space, and one angle is required to represent the angle orientation of the object. So it will be denoted by the S. So R2 times S1 is the C space of the rigid body. Okay, X and Y and this at the angle circle. Okay, let's take the point in the plane. In this case, R2 is enough because it takes the two coordinate x and y. Okay. On the other hand, the spherical pendulum, in this case, we need to coordinate such as the longitude and the latitude. Okay, so it is the sphere, surface of the sphere, so S2. Okay. On the other hand, 2R Lava system, it is one R, this is another R, is here. Okay, it is this kind of two angular variable does not make the any cannot be described by using the longitude and the latitude. It means these two variables are independent of each other. It means maybe this angle make the some circle, this angle will make another circle without intersection between both. Let's generalize this kind of a concept, then we will get some torus, not sphere. Okay, so this is the torus, this is the sphere. Okay, let's check the topological equivalence between both. Okay, let's consider the torus and the sphere. If don't cut here, then extend and then make the circle or sphere, then growing, then we can make this kind of a sphere. It means both are not topologically equivalent to each other. Is it right? The 2R system and the spherical pendulum does not show any equivalency in viewpoint of the topology. Okay, so let's assume that S times S will be denoted by the T2. S times S does not have any S2. It's different. T2, in other words, S1 times S1 will be denoted by the T2. The sphere S2 is not topologically different between to the torus T2. So S2 does not imply S1 times S1 because this is the T2. Okay, the PR joint is here. The prismatic will be described by the real number, and the rotation angle will be expressed by the S. So S1 cross S1 times R1 times S1 will be enough to denote the computational space of the PR joint. Okay, let's consider one more mobile robot. Let's consider a mobile robot system. Two wheels exist both sides. Okay, let's take the point here. Maybe the X and Y will be enough, and the rotational angle should be added to express the rigid body on the plane motion. Is right? So it will be denoted by the R2 times S1. Okay, let's add the 2R. This 1R and the second R here. It means S1 times S1. So 3 S1 can be combined to make the torus T3. So mobile manipulator with the 2R robot arm can be expressed by the R2 times T3. Okay, the C space of the rigid body in three-dimensional space. Okay, in here's X and Y and Z is required, and the roll and pitch, maybe roll and pitch will be expressed by using the latitude and the longitude, and then yaw angle will be required to specify the final motion. Okay, R3 times S2 times S1. It cannot be combined as 3. As you may know, the S2 is different to the S1 times S1. Okay. Okay, let's briefly review the computation space representation. Okay, in order to make the computation, maybe we should apply the numerical value. So the better method to manipulate the numerical value will be the vector. Vector implies the unordered list of the variable. Okay, so if you good at the linear algebra, the vector and the matrix can be used as simple notations. Okay. In the case of computation space as simple as possible, the explicit parameterization of the space is one of the good method to represent the space. Okay, consider the space on the sphere with the latitude and longitude coordinate. Okay, it's enough to express the coordinate values, but it has some problem on the north pole or south pole. In here, okay, let's assume that some person is located on the north pole. He in here taking a small step will result in the very big change in the coordinate. Okay, let's assume that we are stay at near the latitude S19, but in here, okay, here, but the longitude, let's take the small step here, the 0 longitude and 118 longitude. The very small step will make the big difference between the longitude. Like this, we can make the big difference. Actually, very small step, but the coordinate value will be changed as a big value. Like this kind of phenomena is called as singularity of the representation. In short, representation singularity. Okay, this kind of singularity appears as a result of the fact a sphere does not have a same topology as a plane. Actually, we are using the real number system. Real number system is based on the plane, but the sphere, including the latitude and longitude, it cannot be expressed in the planar space because we don't have any similar topology with the sphere. Okay, is it right? Please think about this sentence as many as possible. This provides some insight for you. Okay, this kind of we want to this kind of representative singularity to be solved. We can use the two kinds of methods. Use more than one coordinate chart on the space. The other one, use an implicit representation of the space. Okay. In the case of the whenever you have the representative singularity, we can change the coordinate, such as from the sphere coordinate to the cylindrical coordinate. Maybe the singularity region will be different from each other. On the other hand, okay, latitude and longitude has the two variable, but we will add one more. So x, y, z variable is used to express the longitude and latitude in the three-dimensional space with one constraint, the constant r, constant radius. Because the point moving smoothly around the sphere is represented by the smoothly changing xyz value even at the north and the south pole. If you add some implicit variable, then the constraint will be the implicit, but we don't have any singularities, representation singularity. That's the big advantage in using the implicit representation. Okay, let's consider rotation matrix. Maybe you know the rotation matrix has the 9 variable. Is it right? 9 element. In here, every column vector is normal. It means the magnitude of every column vector is 1. So we have the 3 constraints. And one more, each column vector will be the orthogonal. It means the inner product of the between the column vectors will be 0. So we have the 3 more constraints. It means rotation matrix has the 9 element, but it has the 6 constraint. So the rotation matrix is also implicit representation of the space. Okay. Okay, the next topic is about the computation and velocity constraint. Computation constraint and velocity constraint. Okay, let's consider the polar linkage system. Okay. In here, let's add some coordinate. This is the x. This is the y. Okay, first angle will be denoted by the theta 1, and maybe the theta 1 plus theta 2 will make this orientation, and theta 1 and theta 2 and theta 3, and theta 1, theta 2, theta 3, theta 4. So by adding all the orientation will bring the 2 pi radian, such as the 360 angle or degree. Okay, the coordinate of this point can be calculated. These two vectors, these vectors including the 2 elements. How about this point? Maybe this part will be the result of this point. How about third one? Maybe this is the result of the coordinate value of the third point. I'm sorry, 1, 3 is the third point, and the fourth point will be the origin. So by adding a 4 element will be the 0. It will return to the original posture. And one more, the by addition of the 4 element will be the 2 pi, so minus 2 pi will be 0. So as you know, this mechanism has the 1 degree of freedom. Oh, I'm sorry. 1 DOF is obtained for variable from the theta 1 through the theta 4 minus 3 constraint G1, G2, and G3. In here, the first constraint equation is G1, G2, and G3. So we have the 1 degree of freedom. Okay, like this. Actually, the 1 degree of freedom mechanism is enough to be expressed using the one variable, but we are using the implicit parameterization. In this case, 4 variable is used to represent the 1 degree of freedom mechanism with the 3 constraint. Okay, it has 1 degree of freedom because the 4 variable and the 3 constraint. The set of the all solution form the 1-dimensional curve in the 4-dimensional joint space and constitute C space. Okay, maybe you know this concept. Okay, let's generalize. Okay, the column, the variable is the n-dimensional, and the constraint will be denoted by the k-dimensional. So this kind of a constraint is called as Holonomy Constraint. It will reduce the dimension of the C space. Okay, the C space can be viewed as a surface of a dimension n minus k embedded in the Rn space. Okay, let's take the time derivative, partially time derivative of the constraint. G1 element can be taken as a partial derivative, and G1 and the G2, I'm sorry, theta 1 and the theta 2 and the blah blah. I'm sorry, this is the theta n. Yeah. Okay, this is typo. This is also theta n. So G1 should be differentiated with respect to the theta 1 through theta n. So we have the first equation can be expanded by the matrix and the vector. So we can get the 0. Like this, the velocity equation can be described as a compact form like this. This is the A theta, this is the theta dot. Okay, the k-dimensional 0 vectors. Okay, this kind of velocity constraint of the form are called Papian constraint. Okay, if the Papian constraint can be integrated to provide the equivalent configuration constraint, such as the G1 through Gk as the 0 vectors, if you can get it, then it is called as holonomy constraint. On the other hand, if the Papian constraint cannot be integrated, it does not have any configuration constraint. At that time, it is called as non-holonomy constraint. Okay, let's take an example. Consider the omnight. Okay, consider the omnight coin of the radius r rolling on a plane. Okay, the velocity at the contact point will be obtained r theta dot. Maybe it will be the linear velocity of the contact point. Okay, and in order to describe this point, contact point, we need to x and y. It means R2 is required in a plane. Okay, one more. Where the steering angle n pi, rotation angle theta will be required to describe the C space of the coin. Okay, the theta and the pi does not have any coordinate of longitude and latitude. It means it requires pi and theta will be described by the S1 times S1. It is T2. as a result, R2 times T2 is the C-space shape. Okay. Okay. Also, the C-space. C-space has the 4 or dimensional dimensions. Assume that the coin rolls without slipping. The coin must always rolls in the direction indicated by the cosine theta pi and sine pi. Okay, R theta dot will be projected to the x direction, maybe by applying the cosine pi, the y direction. So we have the x dot. R theta linear velocity is decomposed to the x directions. Okay, so x dot minus R theta dot cosine pi will be the 0. Maybe this is the g1. Y dot minus R theta dot sine pi should be 0. This is the g2. 4 variable and the 2 constraint, it has the 2 degree of freedom. You right? Okay, so let's apply the generalized concept of constraint. Okay, for this purpose, let's introduce Q. Q1 is x, Q2 is the y, Q3 is the pi, Q4 is the theta. Okay, then let's denote these two G1, D2 equation using the Q variable. Then we have this equation. It means the first element is the round G1, round Q1. This is round G1, round Q2. Okay, like this, we can assign the every element as a differentiated form. Okay, as mentioned before, round G, round Q1 must be the one. Let's integrate both sides. G1Q will have Q1, and remaining term of Q2 and Q3 and Q4. We don't know the exact form of the H1. Anyway, let's take the second one. Round G1, round Q2. Okay, in this case, this G1 is applied. Okay, so round H1, round Q2 remains. It should be 0, according to the previous page. Okay, so let's take the integral from both sides. H1 will be the function of Q3 and Q4. Let's denote as L1. Okay, so this is applied to here. G1 is equal to the Q1 plus L1 as a function of Q3 and Q4. Okay, the third element, round G1, round Q3. Let's apply. Okay, then we have round L1, round Q3 is 0. So L1 should be the function of the Q4. Let's denote it as a K. Okay, so G1 will be the Q1 plus function of Q4. Okay, the last element, round G1, round Q4. Okay, so let's take let's apply this one. Then round K1, round Q4 remains. It should be minus R cosine Q3. Okay, let's take the integral of both sides. Then Q1 as a function of Q4, R minus R Q4 cosine Q3. K1 should be the only function of the Q3, Q4, but it has Q3. It does not satisfy the above condition. Is it right? So no such G1 exists. As the same procedure, G2 does not exist. It means it is not integrable. This previous velocity constraint is not holonomy constraint. It means it is the non-holonomy constraint. It cannot be integrated. Such Papian constraint reduces the dimension of the feasibility velocity of the system, but does not do not reduce the dimension of the reachable space, because it cannot be integrated to provide the computation space constraint. Okay, the typical example of the non-holonomic constraint is the conservation of momentum, rolling without slipping. Okay, The last topic is about the task space and the workspace. Okay, task space. Okay, the task space is a space. Robot task can be naturally expressed. The task space is normally expressed by using the end effector frame. On the other hand, the workspace, a specification of the configuration, the end effector of the robot can reach. Okay, in the case of the 2R, the R1 and R2 is here, the C space will be the T2, not S2, but the workspace will be the R2 as a planar disk. In the case of the R3R, 1, 2, 3 serial robot system, the C space of the planar 3R will be the T3, but its workspace R2, the planar disk. On the other hand, the C space of the spherical or 2R, okay, as mentioned in the previous example, okay, the spherical 2R will be the S2. It's totally different from the T2. Each workspace is also S2, surface of the sphere, using the longitude and latitude coordinate. Okay, the last one, the spherical list, the three rotation axes intersect as a common point. Okay, this kind of list mechanism is described by using the S2 times S1. Okay, longitude and latitude are required, so S2 is required, and one more rotation it will be added to express the list mechanism. Each workspace is the same, S2 times S1. Okay. The last two examples. Let's consider the scalable robot system. This is the fixed base, and the first electric motor is assigned, second one, and the third one, and the post-prismatic actuator is placed here. So to pick up the object, place the object as a pick and place task. Okay, each end effector configuration is completely specified. Okay, XYZ times of the pi. It means 3R times R3 times S1. Okay, maybe the workspace is also reachable point in the R3 times S1. On the other hand, the standard 6R industrial manipulator, the end effector has the spray painting device. Okay, in here, spray painting device, at this axis, it can be rotated. It does not affect any influence, any result change. Okay. So the end effector configuration is completely specified XYZ and low rampage without yaw. Yaw does not have any effect to the spray painting. Okay, each workspace can be defined by the R3 times S2, not T2, because the roll pitch is required to express the latitude and longitude. Each workspace is defined as the reachable point in R3 times S2. Okay. Okay, this is the last page of the chapter 2. You have the homework. Homework number 1. Okay, please solve and submit exercise 2.5, 6, 7, 11, 12, 14, 19, 25, 26, 31, 32 until March 26. Okay, next Thursday. Please upload it as a PDF form after scanning your solution, or email me. If you let me know that what numbers you cannot solve, the due date is the March 23rd. Okay, until then, if you cannot solve some issue, some exercise, let me know that. At the time, I will include the solving procedures in the next lecture. Thank you for